before lunch. Talking about porosity and permeability, and I want to start out by pointing out a very important effect, and that's the effect of grain size on porosity and permeability. Now, I talked a little bit about that this morning, but I want to talk a little bit more about it now, since it's very important for reservoir characterization that you include the porosity and permeability. Well, what you're looking at here is a publication way back in 1996 that I used to illustrate that point about the grain size effect on porosity and permeability. This is a reservoir, well logged from a reservoir in the Gulf of Mexico. Having problems here again. Here we go. Okay, here. Having computer problems here. Okay, well, here's a reservoir in the Gulf of Mexico. With the well logs and so on, and cores were taken in this reservoir, and porosity and permeability plugs were taken, and porosity and permeability were measured. Well, when the data points were plotted up, you get quite a bit of scatter. Now, this is a plot of permeability in logarithmic scale and an arithmetic scale for porosity. But what you see is a lot of scatter and no apparent trends that you can see between porosity and permeability. However, when you plot the permeability against the grain size of the core plug samples on a log-log scale, you get a very nice trend of increasing permeability with increasing grain size. And how that can be explained by the grain size distribution, where here I'm showing three histograms, three frequency plots of three different samples. One sample had a permeability of 5,078 millidarcies, another one 1,957, and another one 102 millidarcies permeability. And so the blue one, the curve here, represents the frequency of distribution of different particle sizes within that one core plug. So in blue, where you have the where you had 5,078 millidarcies, the most frequently occurring particle size here is 0.2 millimeters in diameter for the grain size. That translates into about medium grain sand. The middle one here, where you had the permeability of 1,957 millidarcies, the medium grain size there is fine grain sand, 0.1 millimeter in diameter. of the grains. And the third one, the purple one here, that had only 102 millidarcies perm, it had the smallest grain size, very fine sand, 0.08 millimeters diameter. So you went from medium to fine to very fine grain sand, which doesn't seem like a lot when you're looking at that in the rocks, but the result was more than an order of magnitude difference in permeability because of that small change in grain size. So you went from more than 5,000 millidarcies down to 100 millidarcies over that small change in grain size. So this plus many other experiments that have been run indicate that permeability is very sensitive to changes in grain size. And it's like I pointed out earlier or in the morning, you see that effect quite often, but often when you upscale, if you're building a reservoir model, you kind of take that out and average it out, even though it's incorrect. Well, why is it that you get that sort of trend? I can show it to you with this plot here. Here you're looking in just in 2 dimensions at an area of grains with pores. The yellow are the grains, the purple here are the pores. So what you have here is an area, or we could think of this as a 3-dimensional volume, and let's say you have perfect sorting. All the grains are the same size. So the yellow is going to be your matrix, and the purple here is going to be your pore spaces. Now, if we, and this might be, say, a medium grain sand, something like that. Now, if we go to a finer grain sand, something like this, and look at the same area where we have smaller grains and pores, if we were to calculate the amount of grains to the amount of pores, we would get the same value in both cases. We would get a certain amount of yellow here, in this example. I'm going to change. Okay, in this example, we would get the same amount of grains, ratio of grains to pores, as we would in this example. And so that actually is a measure of porosity because you're measuring grains and pore spaces. So what that means is that porosity does not change very much at all with grain size, but permeability does. And if you look at permeability in this very simple manner, that the permeability is going to be affected by the number of grain-to-grain contacts. Wherever you have a grain-to-grain contact, that's kind of like a permeability barrier, so your fluids won't flow from one pore to the next. And if you count the number of grain-to-grain contacts, you're going to have fewer here and many more here, grain-to-grain contacts. So that's how a geologist would look at porosity and permeability. In other words, now permeability, your fluids are going to have a much harder time flowing through this finer grained rock than through this coarser grained rock, just because you have more of these grain-to-grain contacts. Now, I know that engineers normally have equations for this. Again, us geologists, we're more visual people, and so this is the way I like to explain that phenomenon, why you have that. So the bottom line is that permeability it is very sensitive to changes in grain size. Porosity, not so much. So here an example of the other main parameter that is used in looking at grain size distributions, and that is the parameter of sorting. And a well-sorted sand is one where the grains are of the same size. A poorly sorted sand is where the grains are quite a range of grain size. And then here's one with a muddy matrix, very poorly sorted with a muddy matrix and lots of grains of variable size. And you can see here that this is going to give you high permeability, whereas here you'll get low permeability. Why is that? Because the small grains will get in between the pore spaces and the pore throats and not allow fluids to flow through. So when you have a poorly sorted, quite a wide range of grain size, that will be the effect of reducing your permeability. Now, what I did here is I put this in terms of the bedding. Was it thick bedded or thin bedded? And why I did that is because there is a positive relationship quite often in sandstone reservoirs where the bed thickness is directly proportional to the grain size. In other words, if you have two beds, one that's this thick and one that's this thick, the thicker one will generally have a coarser grain size than the thinner one. What does that mean? It means the thicker one's going to have higher permeability and the thinner one will have lower permeability. So not always, but usually you find that sort of a relationship. And let me show you an example of that. Where here we have a Gulf of Mexico well log, and that interval was cored. The black line here is core, where core was taken, and here's the core description. And yellow is sand, and the brown is shale. And 4 core plugs were taken here, one right there, another one down here, another one up here, and another one over here. Okay, so you've got 4 core plugs, and if you look, if you can see this, the porosity is not very different between those 4, all about 30% porosity, but the permeability is quite different. Here we get 3,990 millidarcies permeability, 4,011, 4,289, and 5,270. Now, if we measure the thickness of each of these 4 beds, we get something like this. And the beds were called bed A, B, C, and D. So if we look at those 4 sands, and we've measured the thickness, and thickness increases downward, meaning that sand D has a thickness of 15.2 centimeters, sand A has a thickness of 7.6. You can see the porosity changes a little bit, but not too much, but here you see a systematic increase downward, it's supposed to be an arrow, systematic increase downward of your permeability. So even in very thin beds, these beds are very thin, you get that sort of relationship. The grain size effect and the bed thickness effect both control your permeability. So if we put that as a process here, we have grain size and bed thickness, and they will control your permeability. Porosity a little bit, but not so much as the permeability. So you've got these direct relationships here. Now, both of these, grain size and bed thickness, are a result of primary depositional processes, okay? And so what that means then ultimately is the depositional environment, or the processes by which the sediments were deposited, ultimately controls your permeability and your porosity a little bit. This is another reason why you need to know the depositional environment when you're trying to build a good, reasonable geological model. So I go back to this picture that I showed before, the effects on water flood and reservoir production as a function of grain size here. And I showed this before. We have a sequence of rock that's this thick, and it's getting cleaner upward. In other words, the grain size is increasing upward. So because of that, when you inject fluids here, the fluids are going to seek out the most permeable beds and travel that way. So when you look at the remaining oil saturation, you get a higher saturation after water flood than you do in the upper part of that bed, because you've had better flushing of the hydrocarbons out of the more permeable upper part of that interval. Whereas down here, it's just the opposite. We have our coarsest grain down at the bottom. It's getting finer grained upward. And so after water flood, our remaining oil saturation is very low, and the oil saturation increases upward where the grain size is finer. And in that case, when you injected the fluid would have, the water would have gone down to the most permeable zone, which would be at the bottom. And again, I stress that what the arrows represent here are increase in grain size here, decrease in grain size there, an upward increase in permeability there as you move up, and a upward decrease in permeability in that case. And the better that you can preserve that change in permeability when you're building your reservoir model, the more accurate your model will be. Unfortunately, oftentimes, one of the things that's upscaled when you're doing upscaling for reservoir simulation is you assign a single value to that sand body. And that's, more often than not, that's going to be incorrect. It's going to cause you to, if you're doing fluid flow modeling, it'll cause you to get erroneous results in your simulation, fluid flow simulation. So here again, decrease in permeability, an increase in permeability gives you a upward decrease in remaining oil saturation after the water flood. And here you have just the opposite effect, an upward increase in oil saturation as the grain size and the permeability decrease. So what do you do when you upscale? You may start out with something like this, for example, now this is a case for just porosity, not permeability, but the same principle applies with the permeability, that this may be the real, in your reservoir, this may be your real porosity stratification. You might have this blue bed with 20% porosity, the green one 15%, the red one or brown one 10%, red one 5%, and 2% down here with this one. But so you take this as a geologist, you take this to your partner who's doing the reservoir simulation and say, well, here's the porosity layering in that reservoir. And the reservoir engineer says, well, you've got 1, 2, 3, 4, 5 layers. That's too many. Our computer won't run 5 layers or it'll crash all the time. Something like that. So your reservoir engineer says, go back and make it 3 layers. And let's try 3 layers if we can run our simulation that way. So we go back and we'll take these 3 layers and we'll call that 1 layer at 5% porosity. And then we'll retain our 15% and our 20% there. So we go back and try another simulation and the computer crashes again. Too much data when you have a 3-layer model. And so the reservoir engineer says, go back and make it a single model. Let's do this easily. So you go back and you say, well, okay, do the whole thing, make it all 5% porosity. And that works in your model. You don't crash your computer anymore. But look what you've done. You've gone from true stratification and you've taken all of that out when you upscale. Okay, so it's one parameter. Well, this is porosity, but like I say, you could do the same thing for permeability. And it's one parameter that is often upscaled in a reservoir, and it's a very important parameter because it affects your, either in this case with porosity, it affects the volume, the volumetrics that you calculate, or in the example using permeability, it affects fluid flow in your simulated fluid flow. So it's something you want to watch out for at any rate. All right, a little bit of geology now to go along with more of the engineering properties of porosity, or the petrophysical properties of porosity and permeability. And let's look more closely now at the rocks to see what causes porosity and permeability in a rock. So we have this process us geologists do that we call diagenesis. And what that means is changes that occur in a sediment as you bury that sediment to greater and greater depths. And there's a number of ways in which you can change that sediment. You can do it by physical compaction, or you can do it by precipitation of cements, or you can dissolve out individual grains, or you can just alter pre-existing grains. So let's take a look and see just how these processes of diagenesis control your reservoir porosity and permeability. So I showed this diagram earlier when I started this module here, that you have these different processes as you vary with depth. You have these different processes. Some reduce the porosity and permeability, and some increase it. So let's just look pictures here. compaction. That's a common process. As soon as you deposit sediment, and then when you deposit another layer on top of it, and keep doing that, as you bury the sediment, you compact the sediment at the bottom, and so by doing that, you reduce the thickness. So here we have T for thickness as these grains, the red, green, and yellow grains, would have been deposited, but after burial, now you see your thickness is much less, your grains are more compacted, so your porosity and your permeability is going to be less. So that would be the process of compaction. Let's look at the process of cementation. If you go bury a little bit deeper, fluids that are in the pore space, water in the pore space, often has dissolved elements in it, and under the right pressure and temperature, you can precipitate those elements out and form a cement. So here we have, for example, I've drawn in blue here a pore space that fluids with dissolved ions would flow through, but under the right pressure and temperature, you would precipitate out, and so you now end up in red here with a cement. So again, by doing that, you've reduced your porosity and your permeability. So that's the process of compaction and the process of cementation. And these ultimately, as it says here, they'll ultimately affect your reservoir quality, your porosity, and your permeability. So let's still continue looking at physical compaction, for example. So this is, you geologists know what a thin section is, where you cut a thin slab of the rock and look at that thin slab under a what we call a petrographic microscope. I don't know if engineers do that or not, but geologists certainly do that. So the slice that is made through the rock is only 0.03 millimeters thick, so it's kind of like as thick as an onion peel. So very thin. And when you look under a microscope, this sandstone here, the sandstone there might look like this under the microscope, where you see all the individual grains in the pore spaces. And of course, it's in those pore spaces where you get your oil and your gas. So let's look at, again, a little closer look at the physical compaction process. And so this might be a series of grains when the sediment is first deposited. You may have some of the mineral quartz grains, feldspar grains shown in brown, shell fragments shown in red, and what we call ductile clay-rich grains that are shown here in purple. After you bury them to some depth, you now bring those grains, by compaction, you now bring those grains closer together, and what will happen will be, for example, the shell fragment might break. You squish the clay-rich grains, so no longer is there pore space there. You squish those two grains together, and so on. So that's the process of physical compaction. Now what you're looking at is one of these thin sections that I just pointed to, one of these thin sections that us geologists always like to look at. And what you're looking at here is a very thin slice of a rock that has feldspar grains in it. It has quartz grains in it, Most of these grains are quartz that you see. This is quartz there, quartz grain there, one there, and so on. But notice and all of this is matrix. This is clay mineral matrix. Now what you see is, if you look really closely, you see the effect of compaction, where the clay matrix, which is very ductile, will wrap around the quartz grains. And so that's a form of compaction that you can see when you look underneath underneath with the petrographic microscope. There's another one here, one over here. You can see the same thing. And so these are indications of compaction after burial. So in this case, you deposited the feldspar and the quartz grains and some clay matrix all at the same time. And then as you buried it and compacted it, the clay matrix, being ductile, just wraps around the quartz grains and reduces the volume of your rock. Another form of physical compaction, I showed this morning, where you had an unconsolidated sand. This one contains about 4 billion barrels of oil in it. And here are core plug holes. You see all there, one here, one there, and so on. Well, when that sand was originally deposited on the seafloor, the grains were like this. They were in a very unstable position. And in fact, you had a porosity of 48% porosity. But with a little bit of compaction, you're going to rearrange those grains into a more stable configuration. And what's that going to do? It's going to reduce your porosity and your permeability. So in this case, you drop down to 26% porosity. And I don't know what the permeabilities would be, but certainly the permeability would be less here than it is in that arrangement of sand grains. Okay, let's look at a little more depth then in chemical precipitation and dissolution and how that affects porosity and permeability. So I just pointed this picture out to you, where with burial you have grains and pores, but if you bury that and fluids flow through the pore spaces, you will eventually precipitate out cement in those pore spaces. Well, here's an example of that. You're looking here at another one of these thin sections of rock, and in this particular case, we've got quartz grain here, another quartz grain there, a quartz grain there. Most of these are quartz grains. And then in white and in blue, you've got pore space. Okay? So this sediment was deposited and has retained a lot of its original pore space. So the porosity and probably the permeability will be pretty good. Now, there's something different about these sand grains, though. And if you look, for example, around the edge, if you follow, you see the outline of a grain. Okay, this was the original grain that was originally deposited on the sea floor. Now, when you buried that grain, you started and you had fluids flowing through here. In this case, those fluids precipitated out quartz. And we call those quartz overgrowths. So all of this here is what's called a quartz overgrowth. And when those precipitate out, what are you essentially doing? You're reducing the porosity and you're reducing the permeability. So this cementation process, this diagenetic cementation process, will reduce your porosity and permeability. Here's another quartz overgrowth right there. Here's the outline of the original grain. Comes around like that. So the overgrowth is pretty small right here, but again, it's reducing because of that precipitation of quartz around the original quartz grains that were deposited. Your porosity and permeability is being reduced with burial. All right, let's see what happens. So that's one of the processes that goes on, that cementation, that in this case is incomplete. If this sand was completely cemented, you'd have no pore space at all. Okay, so it's not completely cemented. So there still is some good porosity and permeability associated with this sandstone. Let's look closer now and see what happens around these contacts of different grains. So here's two grains that are in contact with each other right about there. Well, if you look closely, we have a very high-powered instrument called a scanning electron microscope, and it allows you super high resolution at looking at rocks. So we're going to zoom down now and see what's connecting these two grains together. And this is what we find. Here's the remnant of the separation of the two grains. In other words, there is a little bit of porosity here, a little bit of porosity right down in there. But what has happened is you've precipitated, in this case, you've precipitated clay minerals. And the clay minerals precipitate around the edges of the grains. So right there, this is a grain right in here. Here's the edge of the grain. Here's the edge of this grain. And all of this is material that is precipitated, clay minerals, precipitated, and then in some places connecting. So when you see a lot of microporosity from your well log analysis or something like that, this is a common cause that gives you micropores where you get connection across the two grains of these cements, which is going to affect your fluid flow. And it gives you all the, you take one nice big pore, and now you've broken it down or compartmentalized it into a number of smaller pores. And these will affect your fluid flow as well as your well log analysis. Sometimes, well, now what I'm going to show you, I'm going to look underneath this grain and show you what the surface looks like. So here's the surface, and these are all clay minerals that have precipitated on the edge of that grain. And you see there is microporosity here, micropores, but very small in size, and that will affect your fluid flow. So those are some of the causes of why you get variation in porosity and permeability, and it all goes back to number one, how the sediments were first deposited, and number two, what happened when they became buried into the subsurface. So you had depositional processes up here and diagenetic processes down here with burial. Well, a similar related process is one we call pressure solution. And you may start out with deposition of sand here. And as you compact that sand, the grains will come in contact. And wherever those grains come in contact, that's a point where you're going to have very high pressures. Very high pressures at those grain-to-grain contacts. They're very small. And so what will happen is you can exceed the pressure and temperature very locally such that the grains will start to dissolve around the edges. And what happens to that dissolved material? It goes into solution in the fluids in the pore space where the pressure and temperature is lower, and so you precipitate out. What was dissolved here becomes precipitated in there. So the yellow here is cement that has precipitated by this process of pressure solution. So all these little points here that I've shown by the green arrows, they're all pointing to spots in your sand where you would have this pressure solution and then reprecipitation into the pore spaces. So, dissolution, precipitation of cement. And again, that process goes to reduce your porosity and your permeability. So going back here, do we see any pressure, any indicators of pressure solution? Well, we do here, for example. We have this contact that is really, when you get dissolution and precipitation, you really, they're very tightly bonded. It's almost like welding. If you weld two grains together, you get a very tight bond. And so that's what this pressure solution would be doing here. You've got another pressure solution point here. Another one down here, I think, and one right down there. And there's some others as well. So that's what's happening here in this particular case. Not only do you have your quartz overgrowth, like this overgrowth here, that's going to reduce your porosity and permeability, but you also have the pressure solution phenomena that is also going to reduce your porosity and permeability. So just to give you an example of that, one time I was working with a sandstone that had calcite cement. Calcite is easily dissolved in hydrochloric acid. And so what I did is I took a number of different samples from a core and I weighed samples and then I put them into a jar of hydrochloric acid, and then I came back the next day and all the all of the calcite cement had dissolved. And so I took the grains then and measured their weight, and so I could then calculate by difference the amount of cement, the weight of cement that was holding those grains together. And I did that for a lot of samples of a lot of different grain size and permeability and so on. And not surprising, what you find is that the more cement you have, which is the horizontal axis here, the lower the permeability. That's kind of a no-brainer. Okay, so these were all my data points after my experiment, and so you get a nice trend like that. Increase in cement, decrease in permeability. Same thing for porosity. Here's a soluble cement and your porosity here. And once again, you, with an increase in cement, you decrease your porosity. So things like cement content that we, hopefully the geologists do this when you're doing reservoir characterization, because it's very important to do that. Quite often if you send samples out to a commercial laboratory, the commercial laboratory will do these measurements for you. They'll do the thin, what we call the thin section analysis. They'll tell you how much cement you have, how much pressure solution went on, and so on. So when you get your porosity and permeability report, you often get a report of the pictures of the thin sections, and you can see the porosity and permeability and things like that. Okay, well, if we keep burying our sediment, okay, what I've shown you now is the compaction process occurs relatively shallow depths when you bury a newly deposited sediment. And then cementation may be a little bit deeper. You can also form these clay minerals like I showed in the pore space. But there's another process that can be very important, and it's called here leaching or dissolution of grains, which gives you what is called secondary porosity. There's an example of a grain that has been almost completely dissolved in the reservoir by this dissolution. Now, certain minerals are more stable than other minerals in the subsurface environment. So not everything dissolves. For example, this is a quartz grain. This is a quartz grain here, and it hasn't dissolved at all. It's nice and fresh looking. Another quartz grain down here that hasn't dissolved. But now you see this grain here, and it is a feldspar grain, and the mineral feldspar is much less chemically resistant to temperature and pressure than quartz is. So it will dissolve before quartz will. So here you see just the remnant, kind of like a skeleton. Blue is pore space. And so all you see is a little bit of the remnant feldspar grain and a lot of porosity in there that is this secondary porosity. Now in this case, what it's doing is it's increasing your porosity and permeability. So this process of leaching or dissolution has the opposite effect. It's good for a reservoir in that it increases your porosity and permeability. Here's another one. Here you see a feldspar grain. Almost entirely dissolved. The blue is pore space in this thin section. And here you have the leached feldspar. You can just see little remnants of the grain left, and most of it is open pore space. So now what have you done? You've increased the permeability because, for example, you've now got connectivity, the pore space here and the pore space in the grain. And your fluid can flow through there, and there's connectivity out here, and so on. So you've increased your permeability, and the same would go for porosity as well. So a very important process that if you're looking at logs, for example, a porosity log, suddenly you get a big kick with higher porosity with depths where you wouldn't expect it perhaps. high porosity. This can be one of the common causes of that. Particularly, a lot of fluvial reservoirs often have a lot of feldspar with them. I don't know about your reservoirs, but feldspar is very susceptible to this leaching effect. And so if you have a lot of feldspar grains in your reservoir, you can anticipate that you're going to have this leaching phenomena and secondary porosity. And those will be good target intervals for drilling, because you'll have higher porosity and permeability. Okay, the final diagenetic process that can occur is with deeper burial, where you actually fracture the rock under greater pressure and temperature. So you fracture the rock and you create fracture and matrix porosity, fracture porosity and permeability. Just some examples of fractures. Here you're looking at a bedding plane surface, A, and two sets of fractures that you see. Actually, there's three sets here. One set that goes like this, another one like that, another one like that. So three sets of fractures. And the black stuff here is oil, dead oil, that migrated up into this rock. Here's some more fractures looking from a distance in an outcrop on a bedding plane, and you can see the blocky fracture pattern. Person here for scale. And then here's one, this is an interesting one from England, where a lot of England, they farm a lot of the soils. So all of this is farmland down here, but for some reason or another, they haven't farmed this area here. And you can see these beautiful fracture sets, mainly one like this and one going this way. So those are just some examples of fractures and the porosity and permeability that you would get from those fractures. Okay, well, we can draw some conclusions from what I've been talking about. First of all, care should be taken to know how your porosity and permeability measurements are made. You should quality control either by looking at photographs of your core, see where the core plugs were made, and what rock type the core plugs are from, and if they're all good, no core plugs through fractures or anything like that. Porosity and particularly permeability are controlled by grain size distribution and sedimentary processes. Permeability is more sensitive to grain size variations than is porosity. Porosity and permeability are also affected by burial diagenesis. You either lose porosity and permeability, or in cases of leaching, you can increase your porosity and permeability. And these variations in permeability are really quite important in controlling, say, hydrocarbon distribution and water flooding. Okay, I want to give you an example or two now to illustrate this of reservoirs that I've worked on. And this is one from the North Sea, a reservoir from the North Sea that I worked on some years ago. This is the reservoir. This is a fence diagram of reservoir. And all these vertical lines here are where cored wells were taken. All of those. So I had very good core control for this to study this reservoir. What the operator was finding out was that they weren't getting the production like they thought they would. So it was another one of these cases with a phone call, what went wrong, and so I was able to go and try to answer that question. And so I had all this core control and well log control also, no seismic. And what I looked at was at various properties, various reservoir characterization properties, all the data that I had. I had, for example, I knew the rock types or lithofacies that made up the reservoir. I had core plugs from which I could take measurements of porosity and permeability. And these are porosity versus permeability plots for each of the different rock types. I had the rock, so I could look at thin sections and see what kind of porosity I had, and look at the different pore types, primary pores, secondary pores, so on. And I had the well log. So I had, for example, a gamma ray log, which is a good indicator of lithology. And I could see that we had kind of a cleaning upward sequence, meaning the grain size was getting coarser upward. So your permeability and porosity, particularly your permeability, was getting higher as we went from the bottom of that reservoir to the top of that reservoir. So that was the data that I had to use. Here's the field. It was called Balmoral Field. It's in the North Sea, between Scotland and Norway. And I wrote a paper on this way back in 1991, which were just kind of the beginnings of reservoir characterization, geologic reservoir characterization. Prior to the 1990s, characterization was normally done by engineers, and then geologists, all the geologists wanted to do exploration. But in about the early 90s, geologists started getting into more reservoir characterization. That's where I came along and did that. So here was a paper I wrote in Journal of Petroleum Technology in 1991. Okay, if you look at this picture here, this is an outline of the field, looking down on the field. It's map view. And the oil-water contact runs around the edge here. Here's the oil-water contact. The black dots are all the cored wells. And then the fence diagram, I constructed that based on what I saw in the cores. And what I recognized that there were three types of rocks making up that reservoir. There was a channel sand, there was what we called a fan lobe sand, and then there was a sloped claystone. And those were the three rocks that made up that reservoir. So what I did is, after my core descriptions, I made this fence diagram. Now we would build a 3D model in Petrel or something like that, but back in those days, you made fence diagrams to give you a 3D representation of a reservoir. And so what you have, the different colors here, refer to the distribution across the field of those three rock types. The yellow is the channel sand, and it was the best reservoir. The fan lobe is in orange, and it was a so-so reservoir. And the black, this black band here, was the sloped clay. Very thin, but covered most of the field and could be a permeability barrier. But what I did was I took this data. Well, the first thing I did, I have to tell you the story here. I was working with a petroleum engineer who wanted to build a model, take my geologic model and then put it into Eclipse or something like that. And I was fairly new in the oil industry at that time, so I was very proud of myself that I had worked this field and figured out the geology. And I made this diagram, which is the distribution of the 3 different rock types or facies. So the engineer that I was working with had an office down the hall, and so with my coffee cup in hand, I took my map down, a paper copy of the map, and I took it down to the engineer and said, wow, look at this great map that I've made. And the first thing the engineer said to me was, what is a facies? And so that kind of set me back a little bit. And the next thing the engineer said was, what is a channel sand, what's a lobe sand, and a slope clay? And they said, well, that's a very nice map, young man. So I'll put it into the model. And so I was very happy, and so I went back to my office, very proud of myself. Well, I forgot my coffee cup in the guy's office, you know. So I went back to 5 minutes later to get my coffee cup, and what do you think? I looked in the garbage can. There was my beautiful map that I was so proud of. And I said, what did I do wrong? What did I do wrong? He said, this stuff is in units of measure that I don't understand. There's no numbers here. It's all graphics. And we need numbers when we're building a simulation model. And of course, that's true. Not knocking that, I was learning at that point. And so he said, the engineer said, go back and make me some maps of permeability and porosity and stuff like that. And so what I did is I went back to my office and I decided to break out into what we called flow units. A flow unit being as shown here, a volume of rock subdivided according to geological and petrophysical properties that influence the flow of fluids through it. So you have 2 different rocks with different properties. There are going to be 2 different flow units. And so I recognized 5 flow units in that from my core description. And I called this one E for excellent, this one E for excellent, G for good, PI for poor, and the I stood for interbedded, P sub C, poor, cemented, C for cemented, and P sub M because it was poor because you had a lot of matrix in the rock. And so then I classified the permeabilities, broke out the units, and so the excellent one had more than 1,000 millidarcies perm, good was 100 to 1,000, poor 0.1 to greater than 1,000, 0.01, and impermeable. And I did the same for porosity. I broke out porosity, and the poor flow units had a wide range of porosity, and a smaller range of porosity for the E and the G flow units. I did capillary pressure measurements, and so I measured pore throat sizes. So I measured pore throat sizes. Measured pore throat sizes and brine saturation at 200 psi was another measure. And then various geological qualitative characteristics. So massive sand, channel facies, channel and some lobe facies, channel and some lobe facies, channel and some lobe facies, and a massive claystone and mudstone. So those were my flow units. So then what I did is I went back and I remapped these 5 flow units. And so this was my new map compared to the old map, which was facies. Now you see much more detail, and it's based on numbers. I have ranges of values of permeability, porosity, saturations, things like that. And so I then took that back down to the engineer, and he was very happy then, and put that into the simulator and did fluid flow simulation as to where to put infill wells. Now, there was one thing here that surprised us all, and that's, notice the red here. That's your excellent flow unit. Red occurs up here near the top of the reservoir, but it doesn't go all the way across. In other words, you go from excellent to the orange, which is good flow unit. You've got a lot of the good, but just a little bit of excellent, and the excellent is way up in the northwest part of the field. When you get down here, you've got a lot of orange, which is good, but you've got a lot of green, which is poor reservoir. Now I'm going to go back a few, and I want to show you this thickness map for the reservoir. Here's a thickness scale right there. So I showed you before the oil-water contact. Green is where you had where your subsea structural elevation was less than 6,950 feet. In other words, it was shallow burial. The yellow is 6,950 to 7,000 feet, and the pink is 7,000 to 745. So in other words, where you've got the green, that's the thickest oil column. The yellow is the intermediate thickness oil column, and the pink is the thinnest oil column. Now remember where I just showed you where the best reservoir quality was. Best reservoir quality was up here in the northwest part of the field, even though it's not the thickest. It's actually the thinnest part of the reservoir. So one of the findings we made was don't always just drill the thickest part, but drill, look at your reservoir characteristic parameters and look for your best reservoir quality. So we ended up doing more infill drilling up in the northwest part of the field than we did in the thicker southeast part. Okay, so that was an advantage that we would have never picked up on if we hadn't done our detailed reservoir characterization, in this case putting it into flow units. This is a good time maybe to take a break, okay? About a 15-minute